In this lesson, we're going to finally get around to the title topic of our entire unit, which is permutations. Last lesson, we took a look at something called factorials, and we saw that if we had a bunch of objects that we wanted to arrange, we just had to figure out how many objects it was and take the factorial of that to figure out our arrangements. So, for example, one here, how many ways can we arrange? 8 objects. I'm going to kind of go back to first principles so that you understand where we're coming from and kind of going forward to in this lesson. But we had 8 spots, 1, 2, 3, 4, 5, 6, 7, 8. And our first letter, our first object that we could arrange, we had 8 choices for, and then 7 for the second one because it couldn't be the same as the first. And then a similar logic all the way down here. And since we're choosing a first object and a second object and a third and so on, we're multiplying those together. And we basically saw in our last unit that 8 factorial was a fancy way of writing that. Again, 8 factorial just means we're going to start at the number 8 and multiply every number from 8 down to 1 together until we get an answer. And when I punch that into my calculator, I get out the answer 40,320. Okay, so that was factorials. Now we're moving into something called a permutation, which is a very similar idea. We're still taking things and we're rearranging them into certain orders. The only difference is now we don't necessarily want to take all of the objects. So in that example, we were taking 8 objects and we were arranging all 8. Now we're going to take 8 objects, but we're only going to arrange a few of them. So I chose the word romantic because when I think of permutations, I can't think of anything more romantic in my life. And some of you are probably laughing at that. You have no idea how true it is. But anyway, I have the letters Romantic, and I'm going to point out that they're all different letters, and for now, that's pretty important. We're going to have to figure out how to deal with repeated elements, so the same letters or the same objects in a later lesson. But for now, we have those 8 letters, but we don't want to rearrange all 8 of them. If we did, it would just be 8 factorial and we'd be done. Now, this actually may seem almost easier, especially if we go back to first principles. If we want to make a 2-letter word, and a reminder that I put word in quotation marks in this course. A word is any arrangement of letters. It doesn't actually have to be an English word or a word that actually spells anything, just 2 letters. For the first letter, I can choose any of 8 letters to put in there. And for the second letter, I can put in 7 of the letters. It can't be the first one because, well, it's already used. So that just becomes 8 times 7, or 56. So this is a permutation problem. It's taking some, or in some cases, it could be all of the objects that we have, but it doesn't have to be all of the objects. Some of you are probably thinking this is even easier than factorials because it's shorter. You're kind of right. For 3 letters, same logic as before for the first 2, and then our third letter can be any of 6 letters since we've already used up 2 of them. And that should be, I think, 336. Okay, 4 letters, 8 times 7 times 6 times 5-letter possibilities for the 4th character. Okay, so if we take 336 and multiply by 5, I'm getting 1680, and hopefully that is correct. Okay, so that's all it is to the logic behind a permutation, but it would be nice if there was some new math in much the same way that when we looked at our factorial originally, the logic of 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 wasn't very hard, but it would be nice to have a button in our calculator that would deal with this instead of having to type in all of that every time. And we saw that there's a factorial button, the little exclamation. So similarly here, there's going to be a button that we can hit to do these kinds of questions. Now, before we go any further, I will point out that there is some notation here that's fairly important to us, as well as some terminology. And we'll start off by just mentioning that our permutation equation is this. This is definitionally true. So the notation Pn, R, which you may also see written in other sources as NPR, which is what it shows up for on most calculators, your calculator button, but we're always going to use the PNR. And that notation just says we're going to do a permutation where we have n objects and we're going to pick R of them. So in the case of the question we just did above, we had 8 objects and we picked either 2, 3, or 4. So that would be P 8, comma 2, or 8, comma 3, or 8, comma 4. And the short form to write that, or the actual definitional equation for it, is n factorial, which would be arrange all of them, divided by n minus r factorial. So again, I'm just going to kind of go up a little bit and show you that for the first one, the 2-letter version, we did 8 times 7. Well, that's the same thing as 8 factorial, but then without the 6, 5, 4, 3, 2, 1. So that's 8 factorial divided by 6 factorial, which is 8, or n, divided by n minus r factorial. Likewise, 3 letters, 8 times 7 times 6 is 8 factorial, but then we divide by 5 factorial because we don't want the 5, 4, 3, 2, 1. And finally, with the 4-letter word, we have 8 factorial, but we don't want the 4, 3, 2, 1 at the end, so we would take 8 factorial divided by 4 factorial. And for our purposes, and you may not see this necessarily in other books or courses, but we're going to refer to that as n pick r. So in this case, with a 3-letter word, for instance, it would be 8 pick 3. And a reminder that when we're doing these, the order matters. Whether I choose the letters ROM from romantic, or MOR, or ORM, or OMR, yeah, I think I'm getting a bunch of them mixed up here. Either way, the order of the letters, the order of the arrangement of the objects does matter. That's what makes it a permutation. In our next unit, coming up, 2 units coming up, in our unit on combinations coming up, we will be taking a look at what happens when the order does not matter. But for now, let's just take a look at this. So we're going to go back and basically do the same idea as above, except we'll use the new notation. So we had 8 letters and we wanted to pick 2 of them in order. So I write that as 8 pick 2. Now in your calculator, you're going to have to play around a little bit. On my calculator, I would hit the letter, or the number 8, and then I would have the NPR button, and then I would do 2, and then the equals sign. So play with your calculator a little bit. If you're getting the same answers I have, you've figured it out. And if you haven't, you may have to investigate a little further, but usually it's put in the N, hit the NPR button, and then put in the R and hit equals. So on my calculator, I'm going to hit 8, and mine happens to be second function over the 9, but whatever it is on your calculator, 8 NPR2 equals, and my answer is 56, which if you scroll up a little bit, you'll realize is the same as the one that we just did in the previous example. 8 pick 3, again, 8, NPR button, 3, and you get 336, same as we did before. And 8 pick 4, is 1680, the same as it was before. Okay, if you want out the side, I can write down the other version of this. According to n pick r, that's n factorial, which in this case is 8. And on the bottom, we have n minus r factorial. So 8 minus 2 is 6 factorial. And again, reminder that the 6 factorial on the bottom makes the 6, 5, 4, 3, 2, 1 go away from the above one. So it's just 8 times 7. And likewise, this is n factorial over n minus r. And this one is 8 factorial over n minus r. All right, that's pretty much all it is to doing these questions in your calculator. Know how many objects you have and how many you want to pick in order. Now, again, I'm going to do these ones pretty quickly, or try to do these pretty quickly without a calculator, and then we'll verify our answers. So I'm going to do them in kind of 2 different ways to show you. For the first one, I'm going to use the definition. This one is 6 factorial, the n, and the bottom is n minus r. So 6 minus 4 is 2 factorial. Well, that's just 6 times 5 times 4 times 3, and then I don't write the 2, 1 because that cancels with the 2, 1 on the bottom. Truthfully, the 1s always go away. They do absolutely nothing, but either way, the 2 cancels. Okay, so now without even picking up my calculator to do the permutation, 6 times 5 is 30, 4 times 3 is 12, 30 times 12 is 360. All right. I'm going to show you actually a faster way to do it. You'll see that in many of the cases that we do, it actually is a lot faster. And it's essentially just skipping the second line and going directly to the third. So in this case, instead of writing 7 factorial over 4 factorial, I'm going to say that I'm going to do 7, and I'm picking 3 things, so I'm just going to do 3 numbers, 7 times 6 times 5. Now, if I thought about the actual equation, it would be 7 factorial over 4 factorial. The 4, 3, 2, 1 cancel out. This is just a little bit faster. 7 objects take 3 things. 7 times, again, you get to pick the order on these. I actually do this as 7 times 30. It's 210. And the last one actually is very easy if we don't use a calculator to calculate it. It just says start at 11 and take 2 numbers. And that's just 110. Now, if you want, you pick up your calculator, punch them in as permutations, and see if you get the same answers. Hopefully you do. Hopefully I did these correctly. If not, double check to see that you're using your calculator properly. Okay, example 5. An all-star baseball team has 7 pitchers and 3 catchers. How many different ways could a coach pick a pitcher and a catcher to start the game? All right, now, before you give this one too much thought, I'm going to show you what I see commonly in this lesson from my in-class version of the course. They look at the question, they go, well, the big number's 7, small number's 3. We learned permutations today, so it's 7, pick 3. 7 times 6 times 5, 210. We're done. Okay, if you actually read this question carefully, you're not picking 3 things out of 7. You're picking 1 out of 7 and 1 out of 3. This is not a permutation question at all. This is a simple counting principle question. You have 7 choices for pitcher and 3 choices for catcher. There are 21 ways that you could choose a pitcher and catcher to start the game. So you might be asking yourself, why did I put this in if it doesn't have anything to do with permutations? And the answer is you can't just jump to the last thing you learned, plug numbers in, and hope it will work. You actually have to consider each topic. When we get to the end of this unit, as we move further through the course, we're going to learn lots of different problem solving methods. And if all you're doing is plugging numbers that you see in questions into formulas or into ideas that we've done before without thinking about how they work, you probably are not going to get the correct answers. You have to think about what's actually going on in this case. And again, if you stop and think about it, you picture 7 pitchers, you've got to pick one of them. 3 catchers, you got to pick one of them. And then put those together as an and. So that's just 7 times 3. All right, let's keep going. Your band is performing 8 songs at their next concert. How many different orders could there be? Now, I will confess that when I wrote this question, I left it a little bit vague, and in class, I usually give the students a few minutes to try it or ask questions about it before they begin. And one of the questions usually ultimately is, are they playing all 8 of the songs, and are those the only 8 songs they can choose from? And the question does not really emphasize that, but we're going to say, yes, there are 8 songs to perform, and we want to do all of them. So you might say, well, okay, if they're just got 8 objects, or in this case, 8 songs, and we got to do all of them, and we get to choose the order that we put them in, that would just be 8 factorial. And I think we already did this at the beginning of the lesson, this exact one, but that's 40,320. And you're right, it is just a factorial problem. I do want to show you, though, that if you think of this as a permutation, you can think of this as 8, pick 8. I'm not doing this because it's easier. I'm doing this to actually prove a point. This is the same thing. And according to our formula, that should be n factorial divided by n minus r factorial. Well, in this case, n and r are both 8, so subtracting them is that. This and this are the exact same thing, and if 8 factorial equals 8 factorial over 0 factorial, that must tell us that 0 factorial is equal to 1. So this is actually mathematically why 0 factorial equals 1 is one of the definitions we use, the special case for the factorials. It has to be in order for these questions to work out. Either way, if you do it using the permutation button on your calculator, you get the same answer as you would if you did the factorial. In both cases, they're going to be 40,320. Question 7. How many three-letter words can be made from the word quest? Again, quest is 5 different letters. That's important. If they were the same, we'd have to deal with it differently, but there's 5 different ones. So really, we're just choosing 3 letters in order. That would just be a permutation. 5, pick 3. If we punch that into our calculator, 5 pick 3 is 60. And again, I want to show you that you could have done it that way. You could have gone back to first principles and just said 5 choices, 4 choices, 3 choices. That would also give you a 60. Either way is perfectly acceptable. How many ways can the 3-letter word be chosen if it must start with a T? Okay. This time I'm actually going to go to first principles just because I find it a little bit easier in these restrictive problems. So the first letter has to be a T, so there's really only one option there. I have no choice, it has to be the T. That leaves me 4 letters left for this spot and 3 letters left for that spot. And since I'm choosing a first and a second and a third, there should be 12 possible words that start with T. How many ways can the 3-letter word be chosen if it must start with a vowel? Okay, same idea. I'm going to kind of go back to first principles on this one so that we can see how it works. Since we're dealing with the letters in the word quest, the U is a vowel and the E is a vowel. So we have U or E is our starting letter. So we have 2 choices there. Regardless of which letter we put there, there's 4 choices for the second letter and 3 choices for the third letter. 2 times 4 is 8, times 3 is 24 possible words. All right, hopefully you're kind of getting the hang of this idea. Whether we go to first principles or we use the shortcut notation for permutations, we should get the same thing. Okay, moving right along. This last one, there's a little intricacy in it. It's not as hard as most people make it out to be, so just try and play along. Okay, I don't know how many of you know much about the lottery, but one of the more common lotteries out there is called Lotto 649, and it's called that because there are 49 numbered balls and they draw 6 of them randomly. It used to be on TV, they'd actually draw balls out of a machine. I think it's all done digitally now. I'm pretty sure it is anyway. And we want to know basically what what the number of different possible outcomes could be. So I will point out that in the real lottery, the order of the balls chosen doesn't matter, which means that if the winning numbers are 1, 2, 3, 4, 5, and 6, it doesn't matter if they were chosen as 6, 5, 4, 3, 2, 1, or 1, 3, 5, 2, 4, 6, or whatever. They all count as the same winning numbers because they're all put in order when they're published. So what we're going to do is start off by pretending that the order matters, pretending that 1, 2, 3, 4, 5, 6 is actually a different ticket than 6, 5, 4, 3, 2, 1. It's not true, but that makes it a permutation, which is what we're working on. So in this case, we have 6 numbers that are being drawn. And since there are 49 balls, the first one has a 49 different options, the second one 48, 47, 46, 45, and finally 44. I'll be honest, I don't want to punch that into my calculator, but I recognize that this is just a permutation where we had 49 objects and we're picking 6 of them. So whether you do them with first principles or you use the notation doesn't really matter. You'll get the same answer. It's just a little faster to plug into your calculator. So 49 pick 6 is a big number. In fact, it's quite large. Um, oh, geez. Okay, so it's going to be, now you're going to get scientific notation. In fact, I'm just going to make a little note over here. This is 1.0068 blah, blah, blah times 10 to the 10. So if you're not familiar with scientific notation on your calculator, you can look it up. Usually it's just a little exponent or a smaller number in the top right, but you can play with your calculator and see what it is. I am going to do a trick and 10,068 347,520. Okay, that should actually be the exact answer. Now, if you put the scientific notation answer, that's absolutely fine. In fact, that's what I would expect if you were using your calculator for a number that gives scientific notation. Okay. Now, I'm going to point out that the order really doesn't matter with Lotto 649, as I mentioned earlier. So how many ways could we rearrange the 6 numbers once they've been chosen? So for instance, if the numbers 6, 5, 4, 3, 2, 1 are chosen in that order, how many different ways could that appear on a ticket if the order mattered? So it could appear again as 6, 5, 1, 2, 3, 4, or something like that. Either way, all we're doing is arranging 6 numbers. So that's going to be 6 factorial, which is 720. So there's 720 tickets that could have the same 6 numbers on them, just written in different orders, if, again, the order of the numbers mattered, which it does not. So part C is, how many ways can you really win the Lotto 649? Well, according to what we said, we could have, if order mattered, 49 pick 6 tickets. But since each winning set of numbers is going to be represented 6 factorial times, I'm going to divide that by 6 factorial, the number I got in part B, to basically unscramble the numbers to show that the order really doesn't matter. And if I do that, I can punch this into my calculator. It'll briefly give me scientific notation, but it'll go away. So 49 pick 6 gives me the scientific notation number, divide by 6 factorial, and I'm down to 13,983,816. So there's almost 14 million different Lotto 649 tickets, keeping in mind that the tickets will always print the numbers in order from smallest to largest. Order really does not matter. And I'm going to just kind of give you a little preemptive thing here, and that's that when we get to combinations, you're going to see a combination which has very similar notation to permutations, has a slightly different equation. It's got the n factorial over n minus r factorial, which is the permutation, but it has an additional r factorial on the bottom. So it's exactly what we just saw up here. So we just essentially did a manual combination. And a manual combination is just saying do a permutation and then divide by the r factorial to unscramble the order so that order doesn't matter. Again, nothing you need to know right now, but something you'll see when it comes to Unit 3 or Unit 4 or whatever Unit combinations is. Anyway, I'm going to stop there. Try the questions. Let me know if you've got any problems. Otherwise, good luck and have a fantastic day.